Well, it's so great to see everyone. I really like the energy of the room. One of the most enjoyable things in my life is to be able to teach Stanford students. And now I feel, I better teach them well so that when they are alumni like you guys, and they can ask great questions like this.
Thank you so much. Appreciate you.
Okay, so today I'm going to talk about our recent research about positioning and navigation for space. So I'm Professor Gao. I lead the Nav Lab, so that's Navigation and Autonomous Vehicles Laboratory here at Stanford. And then when we think about autonomous vehicles, right, we work on land vehicles such as autonomous driving cars. We work on aerial vehicles such as airplanes, drones. We work on also space vehicles such as robots for space. And then I remember last time I gave a lecture for the All Alumni Day event. I mainly talk about our work about autonomous driving cars. And now that we know autonomous driving cars are already operational, right? They are scaling up. So since I only have 10-ish minutes, so today I decided that maybe we talk about our research more on the space side, right? About some moonshot projects. So in the short period of time, I'm going to briefly cover 4 projects in our group. First is about GPS for the moon, and then 2 projects about the rovers on the moon, and then also finally the neural moon surface maps. So some of them, we actually use the similar approach or technology for autonomous driving cars on Earth, or for navigating airplanes or drones to how to navigate the space robots. And let's first talk about GPS for the moon. When I started this project, I guess probably a lot of you use a GPS to still navigate and locate ourselves on campus. Even nowadays, I still use GPS actually today to find this room. And then actually I myself, I'm an alum as well. I got my PhD from Stanford GPS lab. So I'm very proud that actually GPS is the first PI of the GPS lab is Professor Brad Parkinson. He actually is the father of GPS. So I'm very proud about the GPS system. But then a few years ago when I started the GPS for the moon project, and people will question me, say, okay, we all know that we need the GPS for the Earth. Why do we really? Why this is necessary for the moon? And actually, this is a really, really interesting, fascinating era for the moon. And then after over 50 years, after over half century, the US is going to send astronauts to the moon again. So this is a part of the Artemis mission. So there are multiple phases to send the astronauts to the moon, and the first phase has already completed. And in addition to send the humans to the moon again, there are over 200 missions already planned for the next decade. So there's just really, really a lot of activities for the moon. And then, we could already navigate on the moon back in the Apollo times, right? Astronauts, they found the moon and they could walk on the moon. But then at that time, it was just point to point. So you have something on Earth and you just only need to navigate or locate one thing, like one astronaut on the moon. But think about that. If there are 200 missions already planned, right? There will be astronauts, there will be robots, there will be equipments, there will be all these things, right? And how to be able to locate all these things anywhere on the moon, right? And then some of them, you will see some of our later rover projects, we actually have to navigate in the permanent shadow areas of the moon. So the traditional vision-based method may not work. So because of that, there's we want to build this lunar navigation satellite system. It's basically like a moon GPS. And then different from the Earth GPS, we cannot just redo the same thing because the Earth GPS is very expensive. First of all, the satellites are a lot bigger. They're like a size of a truck instead of, for the moon GPS, we want like a size of maybe even as small as a shoebox. And then the Earth GPS, they use atomic clocks. So, and also because this is such an important system, they say they need redundancy. Each single GPS satellite has 3 atomic clocks just for the redundancy. So currently, just for the GPS itself, there are like about 100 atomic clocks just orbiting in the medium Earth orbit. But for the moon GPS, we want cheaper clocks. So we don't want, it's too expensive to have all these atomic clocks. And then also the Earth GPS, we have a lot of ground monitoring stations. So the key idea is that we can leverage the terrestrial GPS And then we can utilize that for lunar satellite ephemeris correction and clock correction. And then there's also really exciting because I just flew back from Milan. So there was IAC, International Aeronautical Congress conference last week in Milan. And then, so apparently US, the NASA wants to work on this called the Lunar Net. There's a whole like kind of network for lunar satellites. And then NASA wants to work on ESA, European Space Agency wants to work on that. JAXA, that's Japanese Space Agency, also wants to work, and then some other space agencies show a lot of interest. And last week at this conference in Milan, and then ESA announced that they just signed that contract that morning, last week, to launch 5 new satellites as part of this moon GPS system. So that's really something interesting. And then for our group, we have been working on different aspects of this whole like moon GPS in terms of constellation design, in terms of what satellite signals to send to broadcast, how to like design navigation, like ephemeris messages, and all these aspects. Okay, so now talk a little bit more about the moon rover projects. And then, so I'm going to cover 2 projects. One is this one called the Cadre mission. This is in collaboration with NASA JPL. This is really cool because this is the very first mission to send a swarm of rovers to the moon. So in the past, no matter whether if we want to explore the moon surface moon rovers or say Mars rovers, it's always a single rover, like a single robot, right? And then as we know, if we have collaborative robots, like multiple robots or a swarm of robots, there are a lot of nice redundancy, right? And then you also can like cover like a wider areas. So there are a lot of benefits. So because of that, so NASA JPL, they have this mission called the Cadre, and then this is the very first mission to try to demonstrate we can send multiple robots as a swarm to the moon, and then they can collaborate. And so we are very fortunate to have our collaborators working with JPL to work on this. And then this mission, actually, everything is completed. So, and then it's ready to be launched next year to the moon. So hopefully if next year come back, like we can show you some real videos about this. Sorry?
How many?
3. And then, so for us, right, and then because we work on the navigation part, so we have this, we call the physical twin of the sensor suite, navigation sensor suite. So we, have algorithms about how these 3 or 4 rovers can work together and then explore the area. And then, so this is just a demonstration to show that they can automatically, intelligently reshape the formation. And normally, if you want the rovers to traverse the whole area, just to explore the whole area, normally people would think that they will go together, right? I'll say here I show you 4 rovers. But for our algorithm, the rovers actually, they reform kind of more like a kind of square shape over the way, right? Then we try to understand why is this. Then we realize when the rovers in a square shape, they can better help each other. So the geometry of these rovers are better for the localization part. Somehow they kind of intelligently figure out themselves that way. So, and then, so that's about the Cadre, about rovers, swarm of rovers. But these are like a rover is just a tech demo, so it's like quite a small, like a short-term navigation on the moon. And then we also have another collaboration with a different groups with NASA JPL, and then it's about the long-range more kind of capable rover. So this rover, this is a mission concept. So this is going to go explore the south pole area of the moon. So many of, a lot of that area is permanently shadowed area of the moon surface. And then for that, they want this rover to autonomously drive for over about 2,000 kilometers. Currently a lot of the rover, they are not really autonomous, because they always have some human pilots on Earth to try to remotely control or drive that. Actually, some of my former students were pilots, dealing with all these Mars rovers. But this one, they want this autonomy, just like autonomous driving cars, if you have taken some Waymo cars, right? And then what's more, they want long range. They want 2,000 kilometers. So this range of 2,000 kilometers is more than all rovers, like all distance of moon space rovers combined. So this is actually truly exciting as well. And then, so for this mission, when this mission happened, the whole constellation of moon GPS probably is not fully complete yet. So we want to see also with just the current situation, what can we do? And then, so apparently for all missions for space, there's always a communication satellite, because you always need to relay the information back to the Earth or send commands and things like that. So for this mission, there's also called a Pathfinder satellite, and then that is actually also going to be launched very soon, either later this year or next year. And then, so we'll just say, even if we just have one satellite, and then that's actually a communication satellite, not a navigation satellite, orbiting around the moon. Can we leverage that satellite, right? And then, so normally, because this quarter I'm teaching a GPS class, I tell in my lecture, I said, you need at least 4 satellites to do the trilateration. And you have one satellite, it's definitely not possible, right? But then we also think about, okay, but then guess what? The rovers on the moon, they are not in a rush. Maybe not like Stanford students, they always rush from one place to another. They're not in a rush. What if they can afford to just wait, right? So you think about this rover, and it goes somewhere, right? And then we need to know my position now, with, because of I kind of don't know where I am, and I just stay here and then wait. And then of course, at first you only see one satellite, right? And then you wait for a while, and then you can see the trajectory of the satellite over you, right? And that will be equivalent to, you get measurement from this satellite, that satellite, like multiple virtual satellites and multiple virtual measurements, right? And then people may say, oh, maybe you have only good geometry along this plane, but what about kind of perpendicular to that plane? What do you do, right? Okay, so if you also have that request, maybe you can wait a little bit longer, because guess what? The moon satellite orbit, it kind of drift over time. Here I'm just plotting 2 orbital period, right? So if the orbital period drift over time, that's equivalent to, then you have even more measurements from different orbital planes, right? And then, so we basically use this concept, and we actually have this paper to show that, at first, maybe your uncertainty is very high, then if you can afford to wait, and then you can eventually get the accuracy that is good enough to locate the rover. Not only we want to locate the rover, but this also has a lot of science missions, so we can have a really accurate geotagging of the samples the rovers collect from the moon surface. So I think I'm running out of time, so now I'm just going to cover the very last project, hopefully not least, is the neural map for the moon. So, for the urban autonomous driving cars, we use a lot of AI, like deep learning methods, and there's this newer kind of method coming from the computer graphics community called the neural radiance field. You think about this as a way to model the 3D environment using a neural network. So we have done work, say, we even mapped a classroom, we have a new robotics center, room like this, and then using a neural network. So that means traditionally, if you think about you need a 3D model of the environment, you think about our regular map, you pull out the phone, you pull out the map, that's a 2D map, right? And then how to represent that map, it could be lines, or it could be, points, right? And then there's also a way to represent 3D map. You can use meshes or grid points. I see that. And then, so this is just a new way of representing the 3D object, the 3D environment. We use a neural network. So we had some work for urban autonomous driving, and then we call it a neural city map. We apply similar methods, and then to create this neural map for the moon. And then, if we have a better map for the moon, like this neural network representation, we can enable the rovers to do better path planning. And this is in collaboration with Blue Origin, and so they are sending a rover to the moon actually very soon, and then they want the more autonomy for rovers on the moon surface, so they are working with us, using creating this neural radiance map for the moon. So some example path planning. It just shows that if you have a better map, you can do better path planning. So in summary, I lead a nav lab, right? We work on ground, aerial, space applications, but today we mainly focus on these 4 projects about navigating in space, about building a GPS system for the moon, about the moon rover swarm. This is the Kadri mission. This will be launched next year, and the long-range moon rover as part of the endurance mission concept, and finally to create the neural moon surface map for better rover navigation on the moon. And thank you so much, and these are my wonderful students.